My name is Jack Worley, and I am a physics graduate student at Texas Tech University. My research focuses on astrophysical phenomena called novae, which are a type of stellar eruption occurring on the surface of a white dwarf. The white dwarf sits so close to a companion star that it pulls material from its surface onto the surface of the white dwarf. Eventually, this transferred material builds up to a critical pressure and temperature value and explodes in an eruption we call a nova, which is short for stellar nova, Latin for a new star. As the initial outburst settles from a maximum optical brightness, the emitted photon wavelength shifts towards the X-ray, which is characteristic of the cloud of obscuring material expanding outwards, as well as the photosphere, the outer region of a star where photons leave, receding. These two things allow us to see the hot white dwarf, which is still burning some residual matter from the initial outburst. Once the X-ray emission is visible, the nova enters what is called the supersoft source phase, meaning that it emits soft X-rays. Astronomers are interested in this post-eruption phase as well as the initial outburst. To study either of these, we point our telescopes towards the source and we collect spectroscopic data and/or photon count rate data. We utilize both forms in our study, however, the emphasis shifted to the photon count rate data as time went on. The study I led is about a nova from 2023 called V1716 Sco, and it focuses on the X-ray oscillations in the count rate with a period of 78 seconds. We identify this period in numerous different observations and employ a fitting model to see whether or not the period changes over time. Naturally, no telescope is perfect, and few astrophysical phenomena are free of noise or interference from the surrounding environment that may cloud the data. In our case, this noise presented itself as bumps and dips on the 78-second period that introduce errors when trying to make precise measurements. To combat this noise and isolate the true periodic oscillations, we employed a special model that accounts for the changing amplitude to fit the data. If we had not used this model, we would measure a slightly different period in each observation, which is what another group of authors did. However, the method they used and many other researchers use for periodic analysis is susceptible to error when the amplitude of the wave studied changes over time. Because we accounted for this source of error and performed analysis on many different observations, we concluded that the period is indeed fixed at 78 seconds and it does not drift over time. Because of this stability, we suggest that the white dwarf is likely an intermediate polar, which is a classification of white dwarf stars that indicates columns of emission from the north and south poles due to the presence of a magnetic field. V1716 Sco would then be added to a growing category of IP white dwarf stars.